อร์ดแล้วเหรอ
โอเคเอทีพร้อมนะ Okay, good afternoon, everyone. Today we have a individual seminar of 3-point lab, right? For today we have two person for presentation. The first person is Mr. ยุทธการชุ่มมงคล Are you ready?
Yes.
Okay, if you're ready, you can start.
Okay. Are you hear me?
Yeah, it's clear.
Okay. Good afternoon, everyone. Let me introduce myself. My name is Yuttakan Chumongkon. Today, I will present individual laboratory in topics bi-level games whose followers are fuzzy and irrational. In this outline, I will divide the talk into 4 parts. The first part is introduction. Second part is preliminary. Third part is main result. And finally is conclusions. In part of introductions, I will start with net equilibrium and concept of Nash equilibriums. Nash first proved the existence of equilibrium for game where the player preference are respectable by continuous fuzzy concave utility and the strategy set are simplex. And the concept of net equilibrium is no incentive to player to change from strategy because it remains the optimal strategy for each player. In this is structure of game. Structure of game consists player, strategy, and payoff. Next, I will define general framework of strategy game by set G. Set G consists N is player, X is strategy set, and F is cross functions. Next is definition of net equilibriums. Consider N player non-cooperative game. Let Fi be the chord function. Our vector x star equal to this belong to set x is called net equilibrium of this game. If and only if inequality 1. As it is well known fact that classical games don't always model real situations when utility functions are unclear. Wang et al. Studied a new class of generalized abstract fuzzy economy with an uncountable number of agents with fuzzy constant correspondent and fuzzy different correspondent in G-convex space. And they proved some new existential theorem of equilibrium by use parameter of general abstract fuzzy economy. Next, the assumption of perfect rationality that underlie most economy model is far too stiff. Under Lilly and Kenning show clear that the assumption of perfect rationality is far too stiff. They would like a model of bounded rationality as basis for economics analysis. For this purpose, they established the abstract framework that is a model M with parameter class of general game together with abstract rationality function, and they define epsilon equilibria, robustness to epsilon equilibria, and structure stability. Yeah, and next, you prove that the set critical parameter value is very small in topological sense, and model M is structural, stable, and robust to absolute equilibrium of most all uh, of parameter in topological sense. In this is objective of this work. The first is we study the general effect fuzzy economy as well as class of parameter together with relate to abstract rationality function for established model M. And we prove that the model M is robust to epsilon equilibrium if only if structural stable for almost all parameter value. In this is parameter, preliminary. Next, I will talk about upper semicon and lower semicon. The first, we will recall some definition about the continuity of correspondence. Let X and Y both topological space. A correspondent G is said to be compact if G of X is contained in some compact set of Y. In this is upper definition of upper semicon. G is said to be upper semicon on X if for each point, a point X belong to set X, and for every open set U in Y, the set is open in X. The set is X belong to X and G of X is subset U. In this show that in the picture, and lower semicon is same and different for the set is open. The set is open X belong to set X, G of X intersect U equal to empty sets. Next is G is set to be continue on X if G is both upper semicon and lower semi-continue on X. And definition 2.4, if we let X is metric space, Y is a compact metric space, then we set G is upper semi-continue at X belong to set X if and only if Xn convert to X, Yn belong to set G of Xn's, Yn convert to Y, then Y belong to G of X. And lower semicon if and only if Xn convert to X and Y belong to G of X, there exists Yn belong to G of Xn and Yn convert to Y. G is said to be continue at X if and only if for any Xn convert to X, how the distance between G of Xn and X, G of X convert to 0. And this we explain you about the model. A model M consists quadruple capital lambda is parameter space, X is a strategic space, F is fusibility correspondent, and F in index footer correspondent defined by this, and R is rationality function if of lambda and X equal to 0, we call this a full rationality. Yes, and in this is set of epsilon equilibria. Set of epsilon equilibria defined as E of lambda and epsilon equal to the set defined by this, and set of equilibria different set of epsilon equilibria at epsilon equal to 0 and r of lambda and x is full rationality functions. And next we give the Cooper capital lambda and rho b are metric space. Follow definition list. Definition 2.6 tell you about the model M is robustness to epsilon equilibrium. If for all delta greater than 0 and there exists epsilon bar greater than 0 such that when epsilon less than epsilon bar and this row of lambda and lambda prime less than epsilon bar, how the distance between epsilon epsilon equilibrium and equilibrium less than delta. Yes, and the model M is structural stable if equilibrium correspondent E is continuous at set of parameter lambda. Yeah. Lemma 2.8 call about model M is structural stable at lambda belong to set of all lambda, imply that model M is robustness to epsilon equilibrium at lambda belong to lambda if set of all lambda and rho be complete metric space, X be a compact metric space, F be upper semicon correspondent, R is lower semicon functions. Next, we will talk about set fuzzy set and cut set of the fuzzy sets. Let M and N to be to Hausdorff topological vector space, and X is subset M, Y is subset N, B to non-empty convex subset. Since Y is Hausdorff topological vector space, functions capital A from Y into this is said to be fuzzy set on Y. We always denote the collection of fuzzy set on Y by capital F of Y. Mapping from S into capital F of Y is called fuzzy mapping. If F from X mapping to capital F of Y is fuzzy mapping, then F of X is fuzzy set in capital F of Y for each X belong to set X, and this is called degree of membership of point Y in Fx. If capital A belong to collection of all fuzzy set on S and alpha belong to this, then the set this is called to be an alpha cut set of fuzzy set of capital A. Next, I will talk about general abstract fuzzy economy. Gamma equal to xi, yi, ai, bi, and pi in this called generalized abstract fuzzy economy, where for each I belong to set I, xi and yi are non-empty topological space. AI and BI are fuzzy constraint correspondent or fuzzy constraint mapping, and PI is a fuzzy preference correspondent or fuzzy preference mapping. In definition, 2.6 talk about equilibrium for general abstract fuzzy economy. Is a point x bar and points x bar y bar belong to set x times y, and a and b is mapping from x into 0 ones, and pi mapping from x times y into 0 1 such that for each I belong to I is follow property 3 property in this. If we have 3 property in this, we call equilibrium for general abstract fuzzy economy. In lemma 2.11, let x and y be two political space, and a b are closed subset of x. Suppose that fi and f1 and f2 are both lower semicon such that f2 of x is subset f1 of x for each x belong to set A. Then mapping f defined by this is lower semicon and upper semicon is same. We will use the theorem for definition. We will use the theorem for define parameter and model M. The first, let this be a general abstract fuzzy economy. X equal to product xi, y equal to products yi, and AIBI and PI define from AIPI define from this form definition 2.10 and 2.9. Yes, we follow condition are certified by five condition. In the first condition is xi di gamma I and xi prime di prime and gamma I prime are Banach space. Two, second, for each x belong to set x and x mapping to fuzzy set fuzzy fuzzy constraint correspondent this to this are both upper semicon compact mapping with non-empty cross gamma convex value. And third, for each the points belong to set. The point is mapping to preference fuzzy constraint and is a cross mapping with gamma convex value. 4. The set EI defined by this is open in y time x time y. For each x the point of x time y with this and y belong to set this and xi not belong to set this, then there exists the point x times y such that for each I belong to set I and xi belong to set this and constraint fuzzy correspondent intersect preference fuzzy correspondent equal to non-empty set. We can see theorem. Oh, sorry. We can see the theorem 1. The theorem 1 define from definition 2.9 and 2.10. Yes. In this main result, if I have a general abstract quasi economy and I use lemma 2.11 for mix in theorem 1 and can define by this by gi of xy this, and we have gi of xy is upper semicon compact mapping with non-empty code gamma convex value on x time y, and by lemma there exists a point x bar y bar belong to x time y such that point this belong to the set of gi. For each I belong to set I, and get that the point is equilibrium point of general abstract quasi economy. Next, we define capital lambda by the theorem once, and we have this. Yes. When after that we define capital lambda, and we define and define rho, use capital lambda, we get that rho of lambda 1 and lambda 2 defined by this. Oh, sorry. Defined by this. When I define lambda and rho, I can prove lemma 2.1 is prove that lambda and rho is complete metric space, and we can prove lambda and rho is complete metric space and define use parameter of lambda define this model M. Model M equal to lambda xfr, where lambda is a complete metric space and x and y are compact and matrixable. For each lambda belong to set of capital lambda, and for any point this belong to x cross x time y, define f and this, and rationality function is can define this, and we have the model M. We use the model M for proof lemma 3.2 that rationality function of lambda and x is lower semicon at lambda and x, and we have lemma 3.1 and lemma 3.2. We can prove that theorem 2 is let lambda and rho be complete metric space, x and y be a compact metric space, f be an upper semicon correspondent, be a lower semicon function, then M is structural stable at lambda belong to set of lambda, imply that M is robust to epsilon equilibrium at lambda belong to set of lambda. In this talk about this model is structural stable and imply to robust to epsilon equilibrium. Finally, conclusions. In this work, we investigate a new class of general abstract fuzzy economy with fuzzy constant correspondent and fuzzy equivalent correspondent in Banach space. After that, we study the model which parameter class of general abstract fuzzy economy together with an associate abstract rationality function and show that under the compactness and the continued assumptions, the structural stability of the model implies to robustness of the model to epsilon equilibrium. Okay, thank you.
Any question? Any question or suggestion? Okay, if no any question, thank you for nice presentation, Yutaka. Okay.
Thank you.
Can you stop share screen? Okay, next presenter is Mr. Mohammed Arif. You ready? Hello, Arif. Can you hear me?
Yes. Hello.
Okay. If you're ready, you can share screen. Share your screen, please. Hello, Arif. Who can contact with Arif now? Please contact with him. Please contact him for presentation. I don't know what
Hello.
happened.
Hello.
Yeah, I can hear you. Yeah, I can hear you. If you're ready,
Okay.
you can share your screen and present. Let's start.
Okay. Okay. Hello. Can you see my screen?
Yes, I can see.
Okay. Should I start?
Yes,
Hello.
you can start. Yeah, you can start.
Okay. Today I am here to present lab seminar and fixed point lab. So today's topic of my presentation is the proportional Caputo operator approach to the thermal transport of Jeffrey tri-hybrid nanofluid in a rotating frame with thermal radiation. Presenter, it's me, Muhammad Arif. My advisor is Dr. Ruben Sakwatayu, and I'm working in co-advisor Professor Pomkumar, Department of Mathematics, Faculty of Science. Okay. The next First of all, I would like to present the presentation outline. The first one, introduction part, then I will move to mathematical modeling, solution of the problem, then I will explain the methodology, and after that, graphical results and its discussion. Then I will give some concluding remarks, and at the end, I will give some future directions. Research highlights starting from fluid dynamics, then I will move to heat and mass transfer. Then I will talk about fractional derivatives, nanofluid, hybrid nanofluid, and tri-hybrid nanofluid. I will explain a little bit about these concepts. Then I will talk about different shape nanoparticles, rate of heat transfer, and their engineering and medical applications and future directions. Okay, so in introduction, background of the study, the present study, basic definition, brief statement, literature review, problem statement, objectives, application of fractional calculus, and applications of nanoparticles. So starting from the basic definition, I will not take too much time on the definition. I will move to the main problem directly. But fluid are categorized in two different classes, Newtonian and non-Newtonian. And these fluid are categorized by the Newton law of viscosity. If the fluid the fluid which obey Newton law of viscosity, they are Newtonian, and the fluid which do not obey, they are not non-Newtonian fluid. The example of Newtonian fluid are water, air, kerosene oil, and the non-Newtonian fluid are oil, honey, and blood, etc. Steady flow, unsteady flow, and turbulent flow. Steady flow which do not depend on time. Unsteady flow which depends on time. Turbulent flow is the extreme kind of unsteady flow. Okay, heat can be transferred in three different ways: conduction, convection, and radiation. I will explain in detail. Conventional fluid are the fluid which without nanoparticles. So initially, Maxwell carried out experiment, and he find that by suspending some micro-sized particle in the base fluid, because he want to enhance the heat transfer rate. But by doing this experiment, there is the resultant fluid has some sedimentation, clogging, and blockage of narrow channels. So this experiment was failed initially. So after that, in 1995, joined Oregon National Laboratory, USA, he suspend nanometer-sized particle in the base fluid. And this experiment was successful, and after that, many researchers and many new ways were open for this new idea, and it has a lot of applications in different field of sciences and engineering and agriculture. So this was a successful experiment of joy, and after that, a lot of researcher work on it. So these are some applications which I mentioned here on the slides: some industrial, smart fluids, automotive application, agriculture, and biomedical applications. Now, what is hybrid nanofluid? Like a nanofluid was the performance was the hybrid nanofluid was good, but still we need to enhance the heat transfer rate of the working fluid. So that's why the researchers, the scientists, the nanotechnology, who are working in the nanotechnology, they suspend two different particles in single base fluid. So this new mixture formed by the suspension of two new nanoparticles is called hybrid nanofluid. And it can be defined as the base fluid and two more nanoparticles. So we'll give you hybrid nanofluid. Similarly, the suspension of three different nanoparticles to form a mixture, that mixture is called tri-hybrid nanofluid. And now I will give a little background about fractional derivative. So I will say very in simple words that if we write the general form of the derivative of a function, so it has n. So in 1960, Hospital wrote a letter to Leibniz and asked about this n, that what will happen if this n is equal to 1/2. It means fractional. So from there, the idea of fractional was generated, and he said that Leibniz responded that it is a paradox from which one day some useful consequences will be drawn. And now a lot of applications can be by using fractional operator. Many application can be highlighted in various fields. And what is paradox? An unanswerable question or difficult puzzle, particularly one which leads to a so starting from some basic definitions. Initially, many researchers work on fractional, but I will highlight some main definitions. So starting from Raymond Levelli fractional derivative. After that, Caputo came and he gave the idea of fractional. He modified some, and he gave fractional Caputo fractional derivative. Then Caputo and Fabrizio make a new definition known as Caputo and Fabrizio, and recently Atangana and Balino they formed a new definition which was non-singular and non-local kernel. And in the present study, we had highlighted the impact of CPC operator. What is CPC operator? CPC operator is the combination of constant proportional Caputo operator. The Caputo and constant proportional operator. So it gave us CPC. This is my solution methodology. It's by explaining this, the audience will, or the viewers, the listener will understand how we do our research. For the very first, we propose problem. This problem has some initial and boundary conditions, right? This whole system we know mathematical modeling. This we obtain from the mathematical modeling. Once we get the system of equations, then we do some non-dimensionalization process. After the dimensionalization process, we get some dimension in the system of equation along with initial and boundary conditions, right? Then if we want to highlight the impact of any fractional operator, then we apply that fractional operator by generalize the classical one, right? Then transform the boundary conditions and convert PDE into ODE. Convert PDE into ODE means sometimes we use similarity transformation if the system is high nonlinear, and sometimes we use Laplace. In linear system, when we use Laplace transform technique, it transforms the partial differential equation into ordinary differential equation. As in the given model, we consider some rotating frame, so it will give us a complex system of equation. That's why the exact solution of this problem is not possible. So it's very complex. So we use analytical technique. So by using step-is algorithm, limiting solution are obtained for the sake of validation, which will verify our result. Velocity and temperature fields are plotted in various graphs using MathCAD. Results and discussion I will discuss, and then at the end we listed conclusion. So move to the main problem. This is the geometry of the problem, which has, this one is the momentum boundary layer, the first one. The second one is thermal boundary layer, and the fluid passing through this rotating frame that they consider as engine oil, and the condition at the boundary is constant, and the plate is moving with constant velocity. This is the condition at the boundary, right? So using the Navier-Stokes equation and some basic mathematics, we get the system of equation. As the fluid is moving in a rotating frame, so it has primary and secondary velocity. So the primary velocity is represented by U and the secondary velocity is represented by V. So momentum equation 1 and 2 are the momentum equation of primary and secondary velocity. Then by exploiting both equations 1 and 2, we get the system 3, the combining equation 1 and 2. So we get the complex velocity. This complex velocity is represented by F, where F is the combination of primary and secondary velocity, which is mentioned here in the next slide. So where F represents the complex velocity being expressed by F is equal to U plus iota V, where U is primary and iota V is secondary. Okay, and equation 4 represents the thermal temperature equation with thermal radiation. And this thermal radiation, by calculating this thermal radiation by putting its value, and it has T raised to power 4. So by linearizing it using the Taylor series expansion after some simplifying steps, we get equation 5. After that, we set some boundaries and initial conditions. So these are the initial and boundary conditions in the complex form. As in the present study, we consider engine oil as a base fluid, and we suspend 3 different particles, and the shape of all these particles are different. Like copper oxide has spherical shape, aluminum has platelet shape, and titanium has cylindrical shape. And these experimental values are obtained from the website, and then we use these values in our analysis and find out its rate of heat transfer in the working fluid engine oil. So how to prepare the preparation method for trihybrid nanofluid? So the very first step, we collect nanoparticles and base fluid. So the nanoparticles are copper oxide nanoparticles, spherical shape, aluminum platelet shape, titanium cylindrical shape, and these all are mixed in single base fluid engine oil. So it forms the ternary hybrid nanofluid. That's why we call it ternary hybrid nanofluid, trihybrid nanofluid. So this is the mixture of nanoparticles in engine oil. Next, these are some evaluation of the ternary hybrid nanofluid using mixture model. Mixture model was studied by Sahu and Sarkar in 2019. The reference is given. From here, you can see, as we consider 3 different particles: copper oxide, aluminum, and titanium. Now, copper oxide shows the volume fraction of this is the volume fraction of copper oxide. This one is the volume fraction of aluminum, and this one is the volume fraction of titanium oxide. If you want to highlight the impact of copper oxide only, if you want to highlight the impact of copper oxide only, just put this and this value 0. The system will reduce to the nanofluid. If you want to highlight the impact of copper and aluminum, just the volume fraction of titanium oxide, make it 0, you will get the system in hybrid nanofluid. So you can reduce and you can compare nanofluid, hybrid nanofluid, ternary hybrid nanofluid, and by putting all these values 0, you will get the classical engine oil, or the simple engine oil without nanoparticle. Now, as we discussed the different shapes, so different shade can be highlighted here from the expression. Psi represents sphericity of the nanoparticle, and the relation of psi can be expressed as n is equals to 3 over psi, shows that the shape vector of the nanoparticles. Furthermore, this research explains the 3 various kinds of additives with different shapes which have been calculated. First, we consider the values of psi 1 and n1. So the expression then obtained for spherical shape. For spherical shape, psi 1, n1. And for secondly, by considering the values of psi 0.6 and n 4.9, then the expression will be used for cylindrical shape. These are some theoretical results, which by putting in the main definition, we get some numeric values, and that values is used for the spherical, platelet, and cylindrical shape nanoparticles. So this is the theory behind that. So after using that values, we get these values. Look at this. The kinematic viscosity and thermal conductivity, the dynamic viscosity using the mixture model. So the first one shows the spherical shape, the second one shows the cylindrical, and third one shows the platelet shaped nanoparticles. Now, we are using CPC operator. So there are a lot of theory behind constant proportional Caputo operator, but I will explain here in simple words that CPC operator is obtained from the combination of constant proportion and Caputo operator. So the combined effect will give us CPC operator. So CPC operator, when we apply Laplace on it, it will give us the result in this form. And equation 7 can be reduced to equation 8 by incorporating the initial condition, which is 0. F of 0 is 0, so you will get equation 8. So wherever you see this result, the Laplace of CPC will give you this one. So this we will use in our analysis. Now, limiting case are also discussed, like, for example, by putting the rotation parameter 0, fractional operator alpha tends to 1, and volume fraction of trihybrid nanofluid 0, then our fractional trihybrid nanofluid model of Jeffrey fluid in a rotating frame reduced to the solution, classical solution of Jeffrey fluid in the absence of rotation, which was done by Khan et al. 66. This citation is given in the paper, which is already published. Okay, so And this is a limiting case. A limiting case help us to validate our work in the already published work. We can show that our results are accurate. Okay, now as we had a system of the equations along with initial and boundary conditions. So to dimensionalize, as I mentioned in my research methodology, now I'm going to solve the problem. So before solution, we need some dimensionless variable which we can obtain by using Buckingham-Pi theorem. Using Buckingham-Pi theorem, we need we get this equation 9, which is the dimensionless variable. Using these dimensionless variable in the system of equations, we get the transform system of equation, momentum equation in the form of 10, 11, and 12, which is the transform system of equation along with the initial and boundary condition. During dimensionalization, we get some constant which are mentioned here in the slides, and solution methodology. Solution methodology is like first we need to dimensionalize the process, then apply CPC fractional operator, then using Laplace transform, and the inverse was difficult to highlight to find, so we use an analytical method, that is TFS algorithm. By using this algorithm, we can get analytical result from the present solution, from the present problem. Okay, the solution are highlighted through graphs in order to see the impact of various physical parameters clearly. So the first figure shows the impact of fractional operator alpha. At the same time, the impact of trihybrid volume fraction of trihybrid nanofluid, which is increases from 0.02 to 0.04, and alpha is in the range of 0.1 to 1. So if we put alpha 1, it shows the classical solution. So what does it mean? It means that if you look at the graph, the influence of alpha. So alpha represents the constant proportion Caputo fractional operator in a mathematical operator which is used to describe fractional calculus, right? So to understand why this happened, consider a fluid element that is rotating with the frame as the element moves away from the axis of rotation. So what happened? It experienced a greater centrifugal force, which causes its acceleration. So this acceleration results in an increase in velocity, which is proportional to the distance from the axis of rotation. So in summary, this operator can increase the fluid velocity in a rotating frame because it amplifies the velocity gradient, which capture the behavior of fluid experiencing a centrifugal force. Furthermore, results of fractional model of J-free fluid in a rotating frame can be compared with the classical model by taking alpha 1. As in the graph, you can see that alpha equal to 1 shows the classical solution. So the beauty of fractional model, or the beauty of fractional solution, is that it can be compared with experimental values by varying alpha and can get the appropriate solution when required. At the same time, this figure shows the impact of volume fraction on velocity. So the volume fraction parameter refers to the fraction of the total volume occupied by the fluid phase in two-phase flow. Two-phase, why we call it two-phase flow? Because we suspend some nanoparticles in a rotating flow. So by dispersing some nanoparticles, the mixture of trihybrid nanofluid. So when we increase the volume fraction of a phase of the nanoparticle, it can handle the movement of the fluid, causing it to slow down. So this is because of the nanoparticle volume fraction within the fluid, which reducing the overall volume available for the fluid to move through. And as a result, fluid velocity decrease in a rotating frame. Furthermore, the presence of the nanoparticle increase the drag forces. So that's why these drag forces are responsible to reduce the fluid velocity in a rotating frame. Okay, next we have figure 4, which is also highlighted the impact of fractional operator on temperature and volume fraction. So if you look at this figure, the temperature can vary by varying the fractional operator alpha, and by increasing alpha, the temperature of the fluid increases. Similarly, in the second figure, the volume fraction of trihybrid nanofluid, initially it was 0. The 0 means that no nanoparticle was there. So this shows this line. It means that the temperature was so low. So by increasing the volume fraction, there is some resistive forces between the stress force developed, which develop the kinetic energy inside the system, due to which the temperature get higher. And you can see that in a rotating frame, the centrifugal force, you can say that the volume fraction is referred to the fraction of the total volume. So when the volume fraction, the nanoparticle increase, it can enhance the heat transfer between the fluid and the second phase. This is because that second phase means the nanoparticles are bubbles. They can act as a heat transfer agent, either by absorbing or releasing heat as they move through the fluid. So as a result, the overall heat transfer rate increase, which led to an increase in fluid temperature in a rotating frame. So that is the reason that a temperature increases by increasing the volume fraction. Similarly, radiation can increase the fluid velocity in a rotating frame. So it is due to the fact that in a rotating frame, the fluid is subject to the Crowley's forces, which causes a deflection of the fluid in a direction perpendicular to the rotation axis. So when the fluid is heated by thermal radiation, so it expands and becomes less dense, causing it to rise. As the fluid rises, it experiences acrylic forces. So this effect known as the thermal wind and can be observed as atmospherical and oceanic circulation patterns. So thermal radiation can act as a can increase the fluid velocity in a rotating frame by inducing a thermal wind that is deflected by the Crowley forces. So this is all the scenario behind the thermal radiation on the fluid velocity. Same is the case here. Temperature can increase by increasing the thermal radiation. It is due to the fact that the temperature is increased due to the thermal radiation because it can have important consequences for many nature and technological systems. For example, in a gas turbine engine, the combustion process generates the thermal radiation that heats the surrounding air, increasing the temperature and pressure, which in turn enhance the engine performance. Similarly, an atmospheric oceanic circulation system, and many examples are there for the thermal radiation in the temperature system. Okay, next we talk about as we consider the unsteady flow. So unsteady flow can depend on time. So by increasing time or by giving some time to the phenomena, to the fluid flow, it will enhance the speed of the flow. Maybe some extra forces can develop after some time. So due to that reason, the velocity of the fluid get high by increasing the time. Similarly, figure 8 represents the Jeffrey fluid parameter on the velocity of the fluid. So it shows that the Jeffrey fluid is a mathematical model for the fluid that has both viscosity and elasticity, and is commonly used to describe the behavior of complex fluids such as polymer solutions and liquid crystals. So when we discuss it in a rotating frame, so the Jeffrey fluid parameter can influence the fluid velocity in a number of ways. Like, for example, the Jeffrey fluid parameter is a dimensionless quantity. That is a dimensionless quantity. So it can use as a parameter. So describe the degree to the fluid resist deformation due to the shear forces. So when the Jeffrey fluid parameter is high, the fluid is more elastic and resist deformation more strongly. So in a rotating frame, the fluid experiences a centrifugal force that can cause it to deform and flow in certain direction. So in overall summary, the Jeffrey fluid parameter can influence the fluid velocity. So in a rotation frame, by affecting the degree to which the fluid resists deformation and the onset of turbulence and the flow. So due to these reasons, the velocity can accelerate in a rotating frame. And this figure 9 shows the material parameter and the velocity of the fluid. So material parameter can play a vital role in the acceleration of the fluid velocity. By increasing this parameter, velocity of the fluid get high. You can see from the figure, I'm sorry, it can reduce the velocity. Look at the figure, the velocity, the maximum velocity here 2.2, and here the maximum velocity is 1.8. Here the material parameter was 0.5. So the velocity was 2.2. Here, material parameter 1.5, so the velocity is 1.8. So it can control the flow within the rotating frame. And this one is the rotation parameter. Or you can say that figure 10 is used. Figure 10 is used for the rotation parameter. So rotation parameter can affect the fluid velocity, and it can also decrease the velocity of the fluid by increasing this rotation. So by this, sorry, this is like the axis of rotation. Sorry. So axis of rotation, like for example, if we increase it, so it will move, the velocity will slow down. I will give you an example. For example, if you suspend like a small ball with an extensible string and you move it in a circle, so the ball have long string will move slow velocity, and the ball have small string will move with a high velocity. So that is why by increasing R, the velocity is decreasing, and it can be shown from the figure. It can be seen from the figure. Similarly, with GR can affect the velocity of the fluid, and everyone know that these are thermal buoyancy forces, which is used to accelerate the fluid velocity within the boundary layer. So initially the Glacier number was 80, so increasing Glacier from 80 to 90, the velocity of the fluid gets high, and you can see from the figure. These are the comparative analysis of tri-hybrid, hybrid nanofluid, and regular fluid. And you can see from the figure that tri-hybrid nanofluid is more effective in heat transfer phenomena. The highest heat transfer, heat can enhance more by using the idea of tri-hybrid nanofluid. So this research can explain us that tri-hybrid nanofluid is more effective in different thermal systems as compared to the hybrid nanofluid, and regular fluid. And as I discussed that we have done some comparative analysis, so the present solution is reduced to solution obtained by Khan et al., which is the validation of our work, which verify our work. Nusselt number, this is the table for Nusselt number. So Nusselt number can be affected by varying different parameters. Like in this case, increasing the volume fraction, Nusselt number increases, and radiation increase, the Nusselt number decrease. Similarly, time increase. So all these values are highlighted for the Nusselt number. Why? The question is why we use Nusselt, why we need to find the Nusselt number. This is our main target, that Nusselt number can help us to get some results related to heat transfer rate. So this table, from the given table of Nusselt number, we conclude that keeping all the parameters fixed, varying this nanoparticle volume fraction, and it can tell us that by adding nanoparticles, all the mixture of 3 different nanoparticles can enhance the working capability and the heat transfer rate of the engine oil up to 18.728%, which is the great achievement for this. Like it can enhance the heat transfer up to 18%. So this was the main novelty of the present work. In this research, we have 2 main novelties. The one to enhance the heat transfer rate of the considered system, which is in which the fluid is flowing in a rotating frame. The second one is to highlight the dynamics of the fluid using the constant proportional Caputo operator. These are some concluding remarks that the classical model are generalized by applying CPC operator. This is the first. The second one is the comparative analysis have been conducted between the trihybrid nanofluid and hybrid nanofluid, which I already mentioned in the graph, right? This third one is 3 different kinds of nanoparticle were considered, because from the early studies we can get that different shape of the different nanoparticle can affect the heat transfer rate as well. So that's why we check the different nanoparticles and its impact on the thermal transport properties of the base fluid. So from the comparison, it has been calculated that the energy production in the case of trihybrid nanofluid is higher as compared to the other fluid, as I mentioned and as I explained in figures in a very detail. The trihybrid nanofluid is more effective compared to other. It is because of the energy production in case of trihybrid nanofluid is higher compared to the other fluid like hybrid nanofluid, and classical fluid. So the fifth one, right? The comparison highlighted that trihybrid nanofluid is more effective compared to nanofluid and regular fluid, and the rate of heat transfer enhances up to 18.72% by suspending the mixture of 3 different kinds of nanoparticle in a single base fluid engine oil. After that, we also found that the thermal performance is higher for trihybrid nanofluid in engine oil and improve the efficiency of the working fluid here. And the Jeffrey fluid velocity gets higher for high values of alpha, nRT, and lambda 1. Similarly, the Jeffrey fluid velocity declines when increase the values of volume fraction, lambda, and R. And finally, the temperature increases with the increase in alpha, phi, and nR. These are some future directions. Like we can consider cylindrical, vertical plate, rotating plate already considered, moving cylinder, and rotating disc. It depends on our problem, that what kind of problem in future we can, the same idea can be extended to some other geometries. Different boundary condition we can consider. In this, we have constant moment of the boundary. We can consider the ram condition. We can consider the slip condition. Many conditions we can consider in future for the same problem. Similarly, different base fluid and nanoparticles can be considered for various reasons in engineering and medical problems. Similarly, we have taken Jeffrey fluid. Someone can instigate the same phenomena for some other non-Newtonian and Newtonian models like Allred B fluid model, Maxwell model, Walters B fluid model, Kaysen fluid model, many fluids. They can extend this work by considering some different fluid models. In this problem, we have considered the CPC fractional operator. Someone can take the fractal and fractional operator. I already done one paper on that, so someone can extend this work in that. And engineering and biological applications can be highlighted. It depends on the study you consider, the nanoparticle you choose, the base fluid you choose. So all these can be highlighted in terms of engineering and biological applications. It is depend on the base fluid and nanoparticles. Okay, thank you for your time. Any question? Hello?
Okay, any question? Okay, if no any question, everyone please turn on your camera. Okay, thank you for nice presentation, Norris.
You are welcome. Thank you.
Okay, everyone can turn on your camera for take a picture. Right. พี่เปิดกล้องแล้วหญิงเปิดกล้องแล้ว Arif, can you stop share your screen?
Okay.
Please stop share your screen.
Okay, I stop share my screen.
Okay. Okay. พี่เปิดยัง
เปิดแล้วไง
ไหนอ่ะไม่เห็นมีพี่อีฟเลย ไหนวะ
ไหนอ่ะ
อ๋อ นี่ไงเนี่ยเจอแล้ว โอเค
แล้วนะ
one two three again please wait please okay 1 2 3 1 2 3 okay thank you everyone see you
Thank you.
next Monday not next week next next Monday okay
Okay.
okay see you again thank you for joining bye bye